Okay, today's topic is scalar projections, or scalar, the scalar product. I'm getting ahead of myself, of vectors. Okay, now when we talk about two vectors, multiplying them together, like A multiplied by B, and this symbol in between, this is called the dot product. And there's going to be a vector multiplication, the vector product, and then we're going to use a different symbol in there, but this is the dot product of two vectors. When you multiply the two vectors together, you don't get a vector out of it with this scalar product. You get a scalar, which just has a direction. And the definition is magnitude A, magnitude B, times the cosine of the angle between them, if they are drawn tail to tail. Okay. Now, a couple things about this. If the diagram looked like this, here's theta. Since that theta is obtuse, the cosine of an obtuse angle is a negative. So this would have a negative dot product. And there's nothing against having negative dot products. And there are some physics examples, science examples, and one that you may be familiar with is work. Now, it was defined in science. We had, work is equal to force times distance. But they weren't, in basic science, they weren't considered vector quantities. Well, the reason you could multiply force times distance because it was always thinking if this force and this distance were lined up in the same direction. Now, if they're not lined up in the same direction, all that force isn't being used to move the object some distance. So the real formula for work in physics is equal to F dot D. And it's a dot product between, it's a multiplication between force and distance, but it's not a straight multiplication of the force magnitude times the distance because not all of the force is doing work. But I'm not going to spend too much time on that concept for you. All right, now I'm going to do example 14. Now the example says find the angle between these two vectors. Okay. Now, if you look at the formula between, for the dot product, if I can find the dot product in the two magnitudes, then I can isolate for that angle, or the cosine of that angle, and then take the inverse cosine. It's easy to find the magnitudes. Magnitude of A is equal to the square root of 9 plus 4 plus 16, or the square root of 29. Magnitude of B is square root of 64 plus 25 plus 4. Square root of 93. Okay. Now, how do you get this dot product? Now, the book does an example of this on page 520. And I'm going to go through it a little bit, but I'm not going to write it out into the detail that they do because it takes too long. I take the dot product, but I will write this step to demonstrate a couple of things. I'm going to write a couple of things over here on the side. If this is a distribution process, I'm going to multiply this vector with all three of these, and then this one with all three, and then this one with all three. But if you recall that the cosine of 90 degrees is equal to 0, that means when I take the dot product of this with this, it's going to be 0 because I and j meet at right angles when placed tail to tail. So they will... The interaction between the 3i and the 5j produces no value on the dot product because those two they work at right angles to each other, and the definition makes that 0. Similarly, the 3i and the negative 2k will give you 0. And when you go through this whole process, the only values that are going to contribute to the dot product are the 3i dotted with the 8i, and then the 2j dotted with the 5j, and then the negative 4k dotted with the negative 2k. Okay. Then, by definition, magnitude A, magnitude B, well, magnitude 1, magnitude 2 times the angle between them. Now, if you got I and I, they both work in the same direction. The angle between them is 0, so the cosine of 0, as you recall, is 1. So this is 24. Okay? And then similarly, J and J work in the same direction. That's 10. Now, negative 4K and negative 2K, there's a little bit of difference with the negatives. But since these are both negatives, they're both pointing in the same direction. Now, if one was positive and one was negative, then we would have this situation, and the angle between them would be 180 degrees, which is negative 1. So the dot product can be negative, of course, but in this case, that's not true because they're pointed in the same direction, so that's a positive value as well. So adding 24 plus 10 plus 8, we get 42. All right, that's the dot product. Now to find the angle, which was asked for, cosine of theta is equal to the dot product, 42, divided by the square root of 29 times the square root of 93. So if I take the inverse cosine, theta is equal to the inverse cosine of 42 over square root of 29 times square root of 93. That is approximately 36.0 degrees. All right, now this is, I think, one of the most useful concepts in three-dimensional geometry and three-dimensional analysis is the idea of finding angles between objects using dot product. It's a big thing now, and especially since we can find obtuse angles, because if this dot product turns out to be a negative value, you know that the angle between them, the two objects, is obtuse. So that's an important concept, and we'll have with the cross product is based. There's a sign component, element to that, but it's not as useful. And like we found before, law of sines and law of cosines back in the triangle days. Using the law of sines was risky because you didn't know if you're going to get a positive or an acute or obtuse angle. In 3 dimensions, it's even more risky because you have no clue what these things look like. You're relying on the math to see how things work. Okay, another topic for today is projections. Now, projections are a very important topic in 3-dimensional analysis because a lot of the distances between objects can be found by projections, particularly scalar projection. Now, we're going to cover both scalar and vector projection, but the scalar projection is going to be a bigger thing. All right, let's say I have 2 vectors, and here's the background on this one, A and B. And this is where the idea of a projection comes in, if I sort of shine a light down here and project A onto B, I get sort of a shadow of A onto B. That distance right there is called the scalar projection of A to B. Now the book just writes P, like so. I'm going to write this, the projection of A to B, because the projection of A to B is different than the projection of B to A, and here's why. If I redraw this diagram and I project B onto A, do this with green, I'm going to have to extend that so I can then draw this perpendicular. That is the projection of B to A. Now, this is obviously a bigger value than that one. They're not the same amount. And that's why you really should write it like this, because A to B is different from B to A. If nothing, I mean, the P, I guess we could leave, but I always write the whole thing out. Okay, now this is the vector projection of B to A. Okay, now problem number 24, which is one of your homework problems, or your assignment problems, but I'm going to do it for you. It says, show that this formula, this shortcut to find the projection works. Okay, so they say here the projection, and is A to B they want to show is equal to A dot B divided by magnitude of B. Pardon me. Now, people have told me in the past that this is sort of counterintuitive, that we're going to project A onto B and we're dividing by magnitude B. How does that work? Well, if you look up here, this amount is magnitude A cosine theta. Because of this right triangle up here, that's the hypotenuse, and this leg is A cosine theta. So the scalar projection of A to B is A cosine theta. Now recall the dot product of A dot B is magnitude A, magnitude B, cosine theta. Now, to make that look like A cosine theta, if I divide that by magnitude B, I have A cosine theta. So that is the dot product divided by B. So this projection of A to B is the dot product itself, which is this stuff up here, divided by B. So that's why this is valid. Now, the second part of this is the vector projection of A to B, they say, is A dot B over the magnitude of B squared times vector B. Now, that's because, let's look here. This would be the vector projection of A onto B. Now, that's a vector that's pointing in the direction of B, but has this length. So the vector projection, another way of writing this, of A to B, and this is the way the book writes it, is equal to this amount, the scalar projection of A to B, times a vector, and they use U, but I use B hat because B hat, we've talked about this terminology. B hat is a unit vector in the direction of B. Okay, well, this is that, A dot B over magnitude B. B hat is vector B divided by its own magnitude. So that's where this formula comes from, A dot B over magnitude B squared times vector B. Okay. All right, let's do an example. Problem number, I think I can squeeze it in down here, 26. Okay, problem number 26. Let me get my notes. Here we are. Okay, so we're given R. They change up to R and S. 3I plus 2J plus 5K. S 7I minus J minus 3K. And part A says find the scalar projection of R to S. Well, that's going to be R dot S over magnitude S. Well, you need magnitude S. Magnitude S is the square root of 49 plus 1 plus 9, or the square root of 59. R dot S, we need R dot S. Okay. Well, let's find R dot S. We'll put that right over here. Is equal to 21 minus 2 minus 15, which turns out to be 4. So this scalar projection is equal to 4 divided by the square root of 59. Now, what does it represent? It's the amount of R that is projected onto S. Now, I could get this a different way, the way the book says that we can get it, and maybe we'll do that. Okay, but to do it, I would need the angle between the two, R and S, and the magnitude of R and the magnitude of S, because then I could figure, or the magnitude of R, and that way I could calculate that quantity. All right, so if I found the magnitude of R, which would be the square root of 9 plus 4 plus 25, 29 square root of 38. All right, I could then find the angle between them, inverse cosine of the dot product, 4 over the square root of 38 times 59. All right, now this amount is equal to this magnitude multiplied by that cosine. Well, I could actually, it's probably better to write this instead of inverse cosine, right? Cosine theta is equal to this. Okay, so the projection of R2S is equal to magnitude R times cosine theta. Well, it is cosine theta, so this would be the square root of 38 times 4 over the square root of 38 times 59. Those will reduce, and you get 4 over the square root of 59. Okay, let me see. I want to say part B of this question says find the vector projection of R2S. Well, according to this formula, that's equal to A dot B, or R dot S, over magnitude S squared times S. We know that. That's 4 magnitude of S. That's 59 multiplied by S, which is a vector. So that's 7I minus J minus 3K. All right, you can leave it like this, or you can distribute it through. Now, we can also get this by taking this amount and multiplying it by S hat. Now, S hat would be this vector divided by the square root of 59. So if I multiply that through, you'll see that that works out to exactly here. Okay, we have one more topic to discuss, and that is problem number 20, which is one of your homework problems. And problem number 20 is extensive, and it's based off of this diagram. Let's see if I can get this into the screen, into the frame. All right, and I've posted this diagram so you can use it. Now, it's like an A, B, C, D, E type of problem, and they give you some. And I would encourage you to just. I had to actually draw a couple of these lines in there because they were kind of very faint when I printed it out. I don't know if that'll happen to you when you do it, but okay. So problem number 20, it starts out by giving you a couple things. It says, all right, here's. They label vector H. It says, all right, H is equal to 20I plus 45J plus 0K. Well, the problem is it's a house, and they're asking you questions about the construction of this house and the angles that have to be cut in order to get these pieces of wood to fit together. Well, if this is 20I, 45J, and 0K, that means that this point right here is 20, 45, 0. And they also label vector V, and you can see it in the diagram, and it's given as 10I plus 35J plus 8K. Well, then that means this point is 10, 35, what was that? 8. I'm sorry. Okay. Well, then you can figure this vector by a displacement vector. This point right here is easily found. That's right, and the book said that, and it actually has the axes drawn in. I didn't do that, but this is the origin. Okay, so this is the y-axis. So that point only has a y coordinate, so that's 0, 45, 0. All right, so you can figure this vector, you can figure this vector, and you can figure that angle between them. And that's some of the things that you have to do. But I think it would be good for you to print this out and use this as you do your homework. Okay. All right, so here, this is your homework. This is your assignment, let's say. I may have gone off screen with that 0, 45, 0. I don't know if I did. Let me rewrite that, because this one wasn't portrait, it was landscape. All right, so we did 14, so you'll do 13. You still have to do 20. This is number 20. Number 25, because we did 26. And I want you to do number 30 as well. I haven't talked about that. That's finding some angles involved with a cube. All right. And this is quite a bit of work, and I mean, this is a longer video, and so this will be a 2-day assignment, and I think that's working out all right. So tomorrow I won't post another video, and you'll just have you can just continue to work on this, because there's quite a bit involved here. All right, well then I guess I will have something for you on Wednesday.